All right. So in the last lecture, we're starting to talk about the fluid statics. And statics means that the fluid has no velocity. And when fluid has no velocity, we do not have shear stress. So those viscosity forces, will disappear. And the only surface force, okay, will be the pressure force, and the only body force is gravity. And we do the Newton's second law on a control volume or system, or you can Newton's second law you can also see it as the conservation of momentum. And by doing this conservation of momentum on a system on that control volume on that xyz coordinates, we derive a equation so-called the pressure general equation for the pressure and height correlations. Okay, is dp dz equal to rho g. Okay, and for special case, if rho is constant, and also if we change the coordinate from z, okay, to this h coordinate, which is called depth h. Remember, and this is where we finish at the end of the last lecture. Know that this h, the direction will be the inverse of z, and we got this pressure height correlations. And be careful about this one, because that this one is only working for the incompressible flow. What the incompressible flow means that the rho has to be constant. Okay, so that's the reason that when we do that integration on the dp dz, okay, this rho we can just take it out. And so with these correlations, in our mind, we can try to use this equation for some to study some fluid statics problem for incompressible fluid. Okay, and one commonly used example for this kind of problem is the measurement equipment for the pressure is called the manometer. Okay, in the last class we talk about the barometer, right? That barometer is only used to measure the atmosphere pressure, and this manometer is you can see that there is a picture here, and we will have a YouTube. Okay, this is a YouTube connected to the gas, to the fluid, which pressure you want to measure. Okay, and inside this YouTube, is filled with some kind of fluid, and we call it manometric fluids. And with this experiment, measurement equipment, okay, we can try to measure the pressure of this fluid at this point. Okay. So what's this? How this equipment works? Okay. So let's first make this problem a little bit simpler. Okay. Let's assume that the fluid inside of this this A region, okay, is gas. It's not liquid. Okay. Let's assume that it's just gas. Well, what's the difference with gas and liquid? When we're talking about the gas, basically their density is small. Okay. So that means that the pressure difference on this vertical region is not that big. Okay. Because rho is not that big. So in these cases, we can just assume that the pressure for this A at this A point here will be close. It will be equal to the pressure at this point A, at this surface A here. Okay, remember that how we get this conclusion is because we assume that this is gas. So the pressure drop due to these steps we neglected. Okay, it's gas. And after we get this pressure at the point of A, right? This is where we want to measure. And it will be, if you draw a horizontal line, okay, on this YouTube. So on the other side, you can have a point called A prime. So A and A prime will have the same elevation, to have the same depth, okay. And based on the equation we have before, that P minus P0 equal to rho GH, because this A point and this A prime point, they have the same elevation level, okay? They have the same depth. So we can immediately see that the pressure at A will be just equal to pressure at A prime, okay? And so now the question is that how we can find this pressure at A prime. It can be simply calculated by using this additional length, okay, this h, this additional depth for this inside of this manometric fluid, okay. So think about this point B here, and the pressure of this point B. So in most cases we will know, because if this tube is open to the atmosphere, so we can just see that the pressure at this point B is atmospheric pressure, okay. And what's the difference between the pressure of this B and this A prime is determined by this depth h. And based on the correlation we derived in the last class, so we can just writing that P at this A prime will be just equal to this PB. In most cases, it will be 1 atmosphere plus this rho GH. And this rho will be the density of this manometric fluid. Okay, G is the gravity and H. So by this way, okay, because PA equal to PA prime and PA prime equal to PB plus this rho MGH, by this way, we can try to measure that the pressure for this gas A by using this PB, the atmosphere pressure plus this rho m times G times H. So after we reading that what this H value will be, we can immediately measure the pressure for this gas at location A. Okay, so just remember that this is only working, okay? This equation is only working if assume that your fluid for that point A is gas, okay? And what if it's not a gas and it's a liquid, okay? Then you may, so that means that the pressure at this location and this location will not be same, okay? If it's liquid, so you also need to consider the pressure drop on this region here. But now it's because it's gas, so we assume that the pressure here and here is same, okay? So this is the theory behind this manometer, okay. And so in the experiments, okay. So there's we need to decide what to use for this gauge fluid, right? Or also you can call it a manometric fluid. And there's some fundamental theory here, okay. And the first thing, important thing is what we want is that we want this value, okay, specific gravity rho times g to be a small value, so that a little bit change on this pressure on this side will result a very large change of the depth on this B side. Okay, this is the first thing. So this can help us to increase the sensitivity of the equipment. And also some other things is for this experimental equipment is that we want to choose that with low surface tension, because those that capillarity effects we mentioned in the last chapter. When we try to read these steps, right? So if there is high surface tension, depending on if they are whited fluid or non-whited fluid. So the level and this fluid level at this point B, they may not be a straight horizontal line. They may have a curve there, so make it very hard to read. So we try to avoid that cases. So we try to select fluid to be with lower surface tension, and also we do not want the cases that the fluid density will be very sensitive to the room temperature, right? Because that if we put this equipment into different temperature, and the density, if the density of the fluid has a large change, so you will also result in that this H value will be reading be different, and some other stuff. Okay, so this is fundamental things behind this manometer. But the basic idea is that after we connect this nanometer to a fluid, especially for gas, by reading this depth difference on the both sides, okay, H, we can quickly calculate the pressure, okay, of the gas we want to measure. Any question for this, guys? No? Okay, so if you understand this, so let's try to do an example problem for this. Please read this first. Okay, so this one is basically is that we have this YouTube here manometer, and after we can use it to read the to test the blood pressure. Okay, and the fluid inside is mercury. Okay, this Hg is the symbol for the mercury. And we know that for body blood pressure, we have a high number and have a low number, right? The high number, the normal range will be 120 millimeter Hg. So that millimeter Hg means that this H here will be 120 millimeter. And the low number is 80 millimeter, mercury. And that means that for the low pressure, if you read it between this high, this type's difference H will be 80 millimeter. Okay, and so this is a conversion things, and we want to convert it to this reading, okay, to the PSI value pressure. Okay, to do that, we're just using the same equation for this manometer we have here. Okay, PA will be equal to PA prime, and plus this so PA will be equal to PA prime, and PA prime will be equal to PB plus this rho times G times this H value, rho G H value. Okay, and okay, and for the density of the mercury, okay. So for this example problem, basically it gives the specific gravity of the mercury instead. So you first need to, if you want to using this, if you want to get this density of mercury, you're basically using the specific gravity of the mercury times the standard water density. Okay, so by this way you convert it to the density of the mercury, and so this will be what we got. And so let's calculate for the high pressure, high number pressure. So we can calculate it. This is some simple unit conversion. Okay, we convert from the this density from the slug to feet cube, and and so because we want to change it to the PSI, right? The PSI units we're talking is pound force per inch square, right? So eventually we need to change this feet to inch, and also that the reading, okay, of this H here is a millimeter, so we also need to change it to inch, okay. And by doing all this, we can change it to the PSI value, okay. So this is just what the final result will be. And the similar things you can also do it for the low pressure. Okay. So what is the example problem telling us? So this example telling us is that this value here, this 120 and 80, this millimeter mercury depths. Okay. Actually, they are just, you can just thinking that this is just the pressure. This unit, okay, it can just be a pressure, means that a unit, a pressure unit. So so basically, if you go to your unit conversion table, okay, so you should be able to using this one to convert it to either the Pascal or PSI or something Pascal or PSI, something to PSI or to atmosphere or to bar, whatever. So this is the cases this is another unit unit for the pressure, millimeter mercury, okay. And also from this nanometer case, okay, you know that what the physics behind this, why this can be, what's the meaning of this, why this can be, thinking as a unit for the pressure, and in some other cases, some other people use that when they're using this nanometer to measure the pressure, sometimes they're using the water instead of mercury. Okay, so that's the reason that in sometimes okay, you may see a unit called millimeter water. Okay, so millimeter water is also a unit for the pressure, and you can convert it to other units of pressure by using this equation here. Simply it could be equal to the rho of water times G times this millimeter value H you read for this millimeter. So you can convert this unit to the pressure or other pressure units. Okay, so this is what the meaning of this example problem. And so let's now try to go. Yes.
I had a question about the other problem. If you look at the bottom for the solution, when they were going from the first line PA prime to the next line PA equals PA prime, they dropped the pressure of the atmosphere or the air. Isn't it supposed to be plus PB?
It's a good question. So it depends on that what this PB value will be, right?
Right. But we assume, I guess, it would be 1 atmosphere.
I think that because that for this question, so this is the equipment to use to measure the blood pressure. I think for those equipment, most times it's not open to the atmosphere actually. So I think you are correct. Okay, if this is open to atmosphere, so you should add 1 atmosphere here. Okay, so I think in this case they just assume PB equal to 0. Okay.
Oh, so I think actually just says it above, and PB is atmospheric and therefore 0 gauge.
Yeah.
Okay, so, never mind.
So this problem is not written very well. So we do not really know if this PP is. He didn't explicitly saying that the PB should be 0, but from what the solution looks like here, PB should be 0. Okay, consider.
Yeah. All right, thank you.
No problem. And another thing you can consider is that even your PB is 1 atmosphere, okay, that 1 atmosphere pressure you're comparing with this value, 120 millimeter mercury, 80 millimeter, is a very small value. Okay, so you can also, if you think in this way, you can also neglect it, because your body, your blood pressure is much larger than the atmosphere pressure. I can tell you, okay, much larger than that. So yeah, so you can, so maybe that's also the reason that so this problem drops this PB. But to make it simple, okay, you can just assume that it's PB equal to 0. Okay. Okay, so let's go to the next question. So this question is a little bit more complicated because that this is another type of manometer. We call this inclined manometer. So it's not really a YouTube thing type. Okay, so please read this problem first, and so we will go through this one. Okay, so for this one, okay, this type is called inclined because we have a tube, okay. This measure tube for this manometer is not vertical, it's inclined with an angle theta, okay. It's connected to a tank, okay, and with inside this tank and this tube, we have this gauge fluids, okay. If there is no pressure, okay, there is no pressure pushed, into this inside this tank, so basically we will have this nanofluid, okay, on the tank and nanofluid on the tube. They will have the same, elevation level. So this dashed line here is the that elevation level, okay, that depth level. When there is no pressure difference on the tank and tube. So in that case, if the fluid at this dashed line on the both sides, so that means that the pressure here and the pressure here is same. Okay, but if you add a pressure here inside this tank, so the fluid on this tank here will be dropped by a small distance, which is called this small distance is h1. the fluid level, okay, depth level will be dropped by H1. And then in the meanwhile, okay, starting from this dashed line here, you know, the fluid, this gauge fluid in this inclined tube will gain a length L. Okay, and if you use this L times this sin theta, you get this, you know, this length, this length here. Okay, which is H2. Okay, H2 will be equal to L times sin theta. Okay, so the question is that, you know, if we can read this L value, okay, remember this L value is starting from this dashed line, not starting from this vertical line here. Okay, then this solid line here is starting from this dashed line here. Basically, it means that it's starting from studied from this equilibrium liquid level, so-called. Okay, and so if we read this level L, we know this number. Okay, what will this pressure will be inside the tank? So if we're using the that pressure depth relationship we have before, right? So we can knowing that this pressure difference between the tank and the tube here basically will be equal to rho. Rho is the density for this gauge fluid, and times the gravity, and times this elevation difference between the tube and tank, right? So in this cases, this elevation difference will be this H1 plus this H2. Okay, so it will be H1 plus H2. And remember that H2 will be equal to, so the problem is, there's another problem, okay, is that in some cases, okay, we do not know this R value, okay, and maybe we only know the what I see. So in most cases, okay, sorry, I'm making mistake. So in most cases, we can read this H value very easily, right? Because it's along the tube, a thin tube. But sometimes we cannot measure that, you know, how much this H1 value will be, how much it will be dropped from this dashed line, right? So the first thing we want to do is that we need to calculate what this H1 value will be. And how to calculate it? To calculate this H1 value, we can base on the mass conservation, because that, you know, if this fluid inside the tank, right, is drop this depth level by H1, right? So the fluid in this region, the mass of this fluid in region, you know, the mass reduced from this tank will be equal to the mass increase inside the tube, right? So this region here, this dashed line, this L region here, the mass of this gauge fluid, which should be equal to the mass fluid drop, you know, on this between these H1 depths. So by doing that mass conservation, okay, so this is the, you know, the mass, okay, be pushing to the, you know, left the tank, and this is the mass, you know, added to the tube, okay, and by doing this way, we can quickly calculate what the H1 value will be, and after we find this H1 value, so we can quickly put it back to this equation, rho L times G H1 plus H2, and H2 equal to L times sin theta, H2 equal to times L sin theta. And so we can quickly calculate the, you know, the relationship between this L reading and the pressure, what the pressure difference will be. Okay. So this is how, you know, how this inclined manometer works. Okay. The tricky part is here is that you need to be aware that when we read this L level, is starting from this dashed line. It's not really the difference starting from this solid line here. Okay. So that's the reason you need to add the depths, this dropped, the fluid dropped here. And this depths for the fluid in the tank drops, okay, should be calculated based on this, you know, the volume of the mass, okay, for the increase, you know, inside this tube. Okay, so after we have this correlation, and the next question is to ask you what the, you know, the sensitivity, right? Manometer sensitivity. So first we need to define this sensitivity, right? So the sensitivity is defined as comparing this inclined manometer with a straight manometer, okay, with the regular YouTube manometer. And for the regular YouTube manometer, right, is you know, if you have if you're reading L, and then the corresponding H will be so this H is so the corresponding. So if you think that if you have a regular YouTube manometer, okay, so the H will be just be H1 plus H2, okay. So the sensitivity is just defined for this inclined one is just L divided by H1 plus H2, okay, cases. And so based on the the result we got for H1, okay, and so you can just simply calculate it based on this correlation here. So this is not very important for us anyway. So the important thing is that how this L value you read for this inclined manometer, is is related to this pressure drop to measure. Okay, so you will see that for this inclined inclined manometer cases, you will have three additional parameters very important. One is this theta, okay, the angle of inclination will affect it, and also that this you can see this is called the diameter ratio between the tube and the tank. It also will affect your result, okay. So forget about this sensitivity, okay. It's not required for that here. And any question for this inclined manometer?
So Professor, we
yes.
won't be tested on sensitivity.
Yeah, just forget that part. That part is out of the scope of this class. Actually.
Okay, fine. And when we're measuring H2, it's from the dashed line, not the line of the gauge liquid.
Yeah.
So we would be able to write the height in terms of H2 and H1, right?
Yeah.
Okay.
Yeah. So this is a really tricky part, okay? Because that this L we read is really starting from this dashed line. It's not from the actual fluid level inside the tank, okay? And this dashed line is the place where you have no pressure difference on this side, on the left and on the right, okay? This dashed line level is the fluid level. So this is the only tricky part. Okay, so now let's go to another type of manometer. So there is a type of, it's not nanometer, it's a manometer, okay? And let me write it. It's manometer. So in this cases, you will have multiple fluids, okay? And so example is that if I have this manometer, okay, and not only one single tube, U-tube, okay, I maybe have multiple these turns, U shape of the tubes, okay, and we have the air here, and then we have water here. Want to measure, and starting this region, we fill this tube with oil, and at the end we fill with mercury, okay, and so in these cases. And assume that this air surface is the location 1, okay? And then this end location is 2 here. And we want to know the pressure difference between this P1 minus TV2. But because that we have so many fluids here, right? And with this different fluid, level, difference. So how we can calculate the pressure difference between P1 and P2? Because P2, you can just thinking that it's the atmosphere pressure, right? So if we can calculate the P1 minus P2, we can know that what's the pressure for this air. So how we can calculate it? So there is a, let me give you the result first, okay? So so this is the equation, okay? How you can find the pressure difference between 2 ponds separated by a series fluid. So basically you're using just, do the summation of this, all the rho I and also all the depth difference of this HI for all kind of fluids. But just from this equation is very hard to know, very hard to understand how to use it, right? So let me give you an example, okay? Using this example, like to show you that how to use the equation. So for this delta P, basically first you write it as from the left to right, okay? So it will be P1 minus P2, P1 is the pressure you want to measure, and P2 is usually the end pressure, which will be the atmosphere pressure. Okay, after you write this way, then you're starting from the right, from location 2 first. You go this direction back. Okay, so you go for first fluid. Okay, you know that the pressure here, okay, P2 here will be equal to this pressure, right? So because that when we try to change from this mercury to oil level, right? So this is where the horizontal level will be. So let me write this as the 2 prime, maybe point A here. Okay. So first it's like so what's the contribution of these types H3, okay, between this point 2 and this point A here, and that is the rho mercury because it's mercury side, right? So that will be rho mercury times H3 times this H3, and so this is 1 over rho times H from here, and because it's going down, right? So because I'm telling you starting from this point 2 and go this way, so in this direction now it's going down. So when you have this going down, since direction is going down, which means that the same direction with gravity. So you're using a plus value here. So this is the first rho times H is a plus rho mercury times H3. Okay, now you know that the point at this point A, and you know that the point of A will be equal to this point of B, right? Because they are in the same line. So the pressure will be going. So you move this your point to measure the pressure directly to this point here, to point B here, and now you go up. Okay, go up, and then you go to this location here. I call it C, and now you have the pressure difference from this B to C, right? With this H2 length. Okay, and this H2 length is for the oil, and now it's because you're going up, you're against the gravity, so you add a negative sign to it. Okay, and then times this rho oil because this yellow part is oil, and with this H2. Okay, so now you get this point C here. Pressure, you know the pressure at this point C, and again, so this point C is the same level with this point D. Okay, so you just draw a horizontal line, so you not go here, and then I want to know that you know the I go here, right, and similarly, okay, I go this point D here, and I can also continue to draw it here. So I know that this D is also equal to this point E here. Okay, C and D and E, they are the same level, right? Same pressure. Okay, and at this point E, so you need to go up again to reach to this point 1, right? So it's going up. So you add a negative sign here and times this rho water because this is water and times this H1. So you add up by starting from this 2 point end point to the starting point, you go through this U tube, and you know it depends on the direction for the pressure, you know, accumulation. Okay, if it's the same direction with the gravity, you have a plus value. If it's against the gravity, you have a negative value. And also that you can move the point. Okay, if they have the same elevation. So by this way, you can using this equation here. So you can know that P1 minus P2 is just equal to this value. Okay, do I make this clear for you? Or you want me to explain this here again? Sorry.
I just have a question. So for once you get to the oil, right? Yeah. The tube going into the water, that's assumed to be air.
You mean after I go to oil here?
Yeah, right when you're there, going down into the water, that's air.
No, this is the water. The hair is everything the water.
Oh, that's water. Oh,
yeah,
okay.
Everything is water. Yeah.
Oh, okay. That's fine.
Because the water connecting this part. Yeah. Everything is water.
Okay, I thought it was air because
it looks
it's like
white, right?
blue. Yeah. Okay, whatever.
Yeah, it's water. It's water.
Okay, and also if we said that there's the atmospheric pressure, this equation doesn't take that into account.
Yeah, no. If it's have 1 atmosphere here, 1 atm here, that means that this value is 1 atm. So your P1 will be equal to this one plus this 1 atm. So this value only give you the
that's just P1,
P1, and P2. Yeah.
Okay, thank you.
No problem. Any other? Do you guys have any questions? So that how to use this equation you have when you have multiple fluids, okay, inside these U tubes. You know, basically you have this summation, just use summation, but you need to be careful about this sign here. Okay, so if you are usually just going from the right to left, okay, when you're going down, you have plus positive sign, and when you move here and going up, then you will have negative sign. Okay, and horizontally and going up again, you have negative sign. So by this equation, so by doing this way, basically we can neglect the calculation, the pressure on this part, the pressure on some, on this part, something. So we have an example problem to use this correlation. Okay, so please read this example problem. Okay, so this problem is that we connect this manometer, okay, multi-flow manometer with two two pipes, okay, two pipes of water, A pipe and B pipe, okay, and we want to know that what's the pressure difference between them, okay. So basically using the equation we read here before, so you will have read this PA minus PB, okay. A is on the left and B on the side, on the right. PA minus PB equal to delta P, okay. And then how to calculate it, right? So the first thing is that, so we need to starting from this point here, because that is water and water on the both sides, right? So you cannot neglect this length here because it's water, not gas. So first thing you need to do, maybe let me using this picture example. You're starting from this point here, because this is the same level with this B, okay? So this is pressure B, okay? First, you from this point, you go to this point F, it's going down, and this water, so it's raw water times this D5, okay? Times, so it's raw water times D5, and it's going down, it's plus positive value. And from here, okay, we know that we continually we go to these steps here. If we go to these steps, we go to this point value, and inside here is mercury, and with D4, so plus another is going down, right? Plus another D4 times raw mercury, so plus another D4 times mercury, and the level here is same and here, so I can just quickly transfer to here, and then I draw a horizontal line here, and going up, and stop here. So it's going up with this additional D3 here, and with this oil. So we need to have a minus raw oil times D3, right? Minus raw oil times D3. And then we can quickly move into here, it's same level, and drop to here again. So this is D2 times raw mercury. Okay, it's going down, so it's a plus value, D2 raw mercury. And then you can move into this point C here, is same line here. And you want to measure for the A, right? So if you see stopping at this location here, so it's going up with this D1. So you need to minus this rho H2O times D1. So by this way, we'll calculate the PA minus PB very easily, okay? And so just bring all the, the density for H2O, for the mercury, for the oil, and with this all distance things, D1, D2, D3, D4, D5, you can quickly calculate the pressure difference, okay? And so this is how to use this equation quickly to calculate it, okay? If this equation we have here, okay, just give you a shortcut, okay? Because that's the way we go, the way, when I follow the passage of the flow from the right to left, we can quickly write in this summation. So this is only a shortcut equation, okay? And if you do not want to use this equation, you can still using the original equation, to calculate the pressure point for each point, okay? So that you can calculate separately. So in this textbook problem, so we have they also give you the second way to calculate it without using this shortcut method. We can still using the original method. You try to calculate the correlation pressure point, pressure difference for each point, A, B, C, D, E, F point. So you have multiple equations, have multiple unknowns, and then you try to calculate the finally you try to calculate the difference between the starting point and the end point, PM and the PB by the manipulation of this one. So it's also you can also possible to do that way, but obviously you can from this calculation you see that you can see that it's a very, complicated way, okay? Mathematically, it's a complicated way. So this method is much more easier than, to calculate the pressure individually for each part of, fluid section, okay? So, any question here? Okay. So this is when only valid when you have multiple fluids, okay? Inside this manometer. Any question? No question. Okay, that's great. So we're talking about this manometer, right? And that is manometer is only what basically the fundamental equation we use to determine the fluid for the manometer is this equation. Okay, this is the and remember this equation we get, okay, is we know that it's only for incompressible fluid, which means that when this rho is a constant, right? So if this rho is not constant, if your fluid density is not constant, then we will not able to use this equation anymore. We have to go back to our standard equation, this one, dp dz equal to minus rho g. And this rho can maybe a function of temperature, a function of the z or whatever. You need to put the variable rho here and do integration on this one to find the pressure. Okay. So one example that when your fluid is compressible fluid, which means that your density is not constant, is air. Okay. Atmosphere ideal gas. Okay. So assume that if you have a, just a atmosphere.
Professor,
sorry.
Can you please upload these? We don't have them.
I uploaded it already.
Oh,
maybe you didn't check it. So on your blackboard, on the PowerPoint session, I uploaded there like 1 hour ago actually. So if because I just created this kind of slides, a few hours ago. So I usually upload it there, at least some 1 hour before the lecture. So if you want to use print it out, you need to be hurry actually. Sorry for that. I will try my best to make it earlier, okay, available. Yeah. You can find it there, okay. All right, so for this one, the case is that if you have the atmospheric air, okay, or you can think that is ideal gas. So the density rho will not be a constant, and the density of rho is determined by the ideal gas of equation of state. And ideal gas equation of state P equal to rho RT. Okay. So if you this is pressure height correlation, the general one, and now rho is not constant anymore. So if I replace this rho in this pressure height relationship with this ideal gas equation of state, so this is the equation we get. dP equal to minus P divided by RT times G times dZ. Okay. But for this one, we cannot integrate this differential equation on P and Z to get the pressure. Why? Because this will introduce a new variable called the temperature. And temperature definitely will also not be a constant value in most cases. For example, even you consider this is the air in the atmospheric air, okay? When you increase the Z, right? When you increase Z, it's like you increase the elevation. When you increase the elevation, your air temperature will also be changing, right? T will also be a function of Z, because that we know that at a very high elevation, maybe 10 kilometers above the earth, above the sea level, the temperature will be much smaller than our room temperature. So this T will also a function of Z. So to really resolve this equation, we also need to know the correlation between temperature and Z. So that if we can write this temperature as a function of Z, so that we can, really solve this equation by the integration on the both sides. Okay. So what's the correlation between temperature and Z? Let's go back to our slides we used before. This when we're talking about this atmosphere, standard atmosphere. Okay. So this is a curve to showing that how the temperature is changed with air elevation. Okay. So you can see that it's not a monotonic trend. Okay. It will the temperature. So on the y-axis, axis is when you try to increase the elevation. Okay. So you will see that the temperature of air, you will from the beginning it will decrease first, and then increase to some level and then decrease again. So you have this something like inverse S curve. Okay. And so let's make the problem a little bit simple. Okay. Let's try to only consider this trend, this part. You can see that this part is like a straight line, right? So basically, you can see that okay, for the air elevation between 0 to 11 kilometer, the temperature will drop with elevation linearly. Okay, so this is, so if we just only want to study the atmospheric air in this elevation range, okay, so we can quickly assume a temperature elevation correlation here. So let's assume that in this region, okay, with altitude up to 11 kilometer, let's assume that is decrease, temperature decrease with elevation, okay, with linearly. So we write that T equal to T0 minus T mg. T0, you can consider this is the sea level temperature. Okay, so now if you bring this equation to this T here, and then for this equation on the left hand side is only a function for P, on the right hand side not only on function of P. So you can divide the P onto the left hand side. So to make the right hand side only function on Z, so you can integrate directly on this equation. Okay, so basically you will get this dP equal to this value. Okay, and you divided P on the both side. You make the left hand side is only a function for P. You make the right hand side is only a function for Z. And now you started to integrate this on the both sides from the sea level to some altitude Z, and assume that the pressure at that altitude is P. Okay, so this is what we want to solve. So you do this integration on this equation. For this one over P, you get ln. Okay, you get this results on the both sides. Okay, ln P equal over P0 will be equal to this G divided by M times R. This R is gas constant. This M is this linear slope of this temperature regarding to Z, and times this ln 1 minus mz divided by T0. So this is the result we get. And further, if you can change this ln into the exponential, and you can write your final result will be this one. Your pressure as a function of elevation for the atmospheric pressure air will be equal to P0 times 1 minus mg divided by T0 with this exponential coefficient G over MR. Okay, and you can further to make this shorter because that is 1 minus mg, right? So 1 minus this mg divided by T0 equal to T0 minus mg, right? So what is T0 minus mg? And based on this equation, we define T0 minus mg is just equal to the local temperature. So you can, if you want to change this Z to the T, okay, you can even write this equation as P0 just T minus T0 over G divided by MR. Okay, so by this way, okay, if you do not know the elevation, but you know the temperature at that elevation, you can also directly calculate the pressure. Okay.
Professor, what's mz again?
This M? Yeah, M, this is this constant. This is the slope. You see that for the atmospheric air, you know that this is straight line, right? So this is the slope of this straight line. Okay, so that's why we write that T equal to T0 minus this mz, right? Assume this is Z location. Okay, so this is just this slope. Okay, this will be given for the problem if you need to solve. Okay, for the problem.
All right, thank you.
Yeah. So this is the cases to showing that how to, using this pressure height relationship in the cases when your fluid density is not a constant. Remember those manometer cases we go through before, that is for the liquid. That is when your density is constant. But for the ideal gas, okay, this is the result you get. The pressure and this elevation correlation Pm as a function of Z. If the cases is that your temperature varies with linearly with the elevation. Okay, this is, remember, this is the condition, when you can use this correlation here. Okay. Any question here? Right? No. So example problem. Please read this problem description. Okay, so for this one, right, we want to so this one, the problem is that we want to measure the atmospheric pressure at different elevation. Okay, so we want to measure that the what's the atmospheric pressure at Denver with this elevation z equal to 5,280 feet, and also the pressure and temperature is given, and also that we want to measure that what's the atmospheric pressure at this wave path. Okay, is a much higher elevation, and also the temperature is given. Okay, and so the pressure here is actually the pressure for the downward is already given with this value. Okay, so now we want to calculate the new the pressure at this new level, and so we just need to using the equation we have before, right? So this P unknown minus this P known will be that will be delta P, right? Will be equal to this P will be equal to this P known times this 1 minus mz divided by T0 over this value. So our question here is that we need to try to find what this m constant, that slope of the temperature drop with elevation, and also, yeah, I think this is the only thing we need to solve, because T0 is given as the, so this is T0, and this R is the gas constant for air is already known, and gravity. So this m value is the only thing we want to know. So first we need to calculate the m, and so m is just the slope of the change of the temperature due to the drop of temperature due to the elevation, right? Altitude. And so you can quickly calculate m equal to the temperature difference minus the altitude difference. So it will give you this value here. And you see that we switch order from, we're using T0 minus T, and on the bottom we're using Z minus T0 because because when we define this m, we have this negative sign here. So which means that the temperature will drop with altitude. Okay, so that's why you see that this order is switched, so that to ensure that this m give you a positive value. Okay, so by this one we can quickly calculate what m value will be. After we get this m value, and we have the gravity, we have m value, I have this gas constant for the air, and you can quickly calculate this exponential coefficient for this correlation here, and so it gives you this exponential coefficient which is 5.55, and finally, okay, you just put everything together into this equation if you know the temperature, and it's showing that the new pressure actually at this higher altitude will pass, it's only 83% of the original pressure in the Denver. So this gives you quickly the pressure change. Okay, and so after you have this pressure change, they also ask you to what's the change on the density, right? to change the change of density, just calculate from the equation of state. Okay. So after you know this new pressure, you can calculate using the equation of state to calculate the density at the downward and density at the valley path, and then you just minor, calculate the density difference between these two. And so on the textbook, they're using an even simpler method. Just assume that, based on the equation of state, so this density changes can be quickly, using this ratio with this, this is a relative change on the density. This is a reference value. So this will give you a value in the percentage. Okay. And to calculate this rho over p rho 0, you can use the equation state to change it to p t0 and p0t. Okay. And substitute the value you have, you can quickly know that the density will be decreased by 14.2%. Okay, so this is an example problem showing you that how to use this equation, to calculate the pressure in the atmosphere. Okay, how the pressure is changing either with the elevation or elevation altitude z, or with the temperature at that altitude. Okay, if you know it. Any question here, guys? No question? All right, so let's go to the next topic, okay? So previously, we just basically try to study the correlation between the pressure and the depth, right? And so now we know that with the known depth, right? Depth, sorry, not depth. With known elevation, with the known depth, we can calculate the pressure very quickly from those pressure depth correlation. But after we calculate the pressure, right, we know that pressure is a stress, and pressure will give you the pressure force. So the next step we want to analyze is that how this pressure will give a force to other body. Okay, especially that if you have an atom submerged into a fluid or some liquid or gas. So we want to know that what that pressure, we calculated from that, due to this depth will given. Okay, what that pressure force will result to on the body submerged into. Okay, for this kind of problem, we will separate it into two types. Okay, the first type is consider a flat plate. Okay, so we have a straight plate, and we suddenly push it on into the fluid, into a liquid maybe, as a better example. And then we want to see that how the pressure force is, applied on the surface of this flat surface. Okay, realistic example is like this water gate of a dam. Okay, this kind of thing. And from this picture here, you can immediately see that, okay, if we put this flat plate, okay, vertically into this water, okay, assume this is water, okay, make it simple, and so the surface of this plate will, subjected to the water pressure, right, pressure force, and in the location very close to the surface, the pressure force is not that big, but the deeper, going down, okay, the deeper position we go, the larger pressure force, this surface will be experiencing. Okay, and so if we using this this water gate for this dam as an example, okay, one side is one side of this surface, this plate surface is face water, another side maybe it's only facing the atmosphere. So if you look at the other side, so they will experience, this surface will experience this universal atmospheric pressure. So we'll see that the location here, the location here, they are the same pressure. They are all 1 atm. It won't changing with the depth. Okay, because for the gas, okay, that changing on the elevation is will not result in significant pressure difference. Okay, and with these cases, what we interested basically is the net force, right? on this x direction. So basically, you can using the force on the left minus the pressure force on the right. So by this way, you can remove this 1 atmospheric pressure, one atmospheric pressure level. Okay, and so you can, this will be your result pressure, profile looks. Okay, how the pressure net pressure force is executing on this surface. Okay, so as you can see, that it's not a constant. It will become larger when these depths become larger. So now the question is, okay, so we know this distribution, right? But when we try to build, when we try to design this water gate, I do not care how this pressure is distributed. I just want to have an estimate that what the overall pressure force will be, right? So it's like I know that is on the top, maybe it's on the top means the pressure force is not that big. On the bottom, the pressure force is larger. So is that possible that we can, make this, parallel forces, okay, pressure forces, making them to a single resultant force. That's we try to using a single resultant force, and also try find a point, okay, and try to find a point location, so that the force and the moment, this location to the bottom or to the top to somewhere moment, this single force and the moment created by this single force will be equal to this overall pressure force. So if we can find that, so we make the problem simpler, because that we can just reduce this surface problem just to a single force, actually, surface pressure to a single force. Okay, so this is what we want to do. Okay, and this force is called the resultant force, and this point location where this resultant pressure force will apply, we call the center of the pressure. So we need to find where this center of pressure will be and what this resultant pressure force will be for this problem. So this is the first kind of problem. And the second kind of problem is not a flat plate, it's a curved surface. Okay, example like if you have a ship, the under, the body under the water is not a curve anymore. Sorry, not a plate anymore. You will have a curve. So this is example here. And so for these cases, if you try to analyzing what the pressure force on the surface under this water, you will see that you will be location, the pressure force, basically will not be parallel anymore, because that the pressure force is always be in the direction of the normal direction of the surface, right? So the direction is also changing. And in these cases, so maybe we can also try to reduce all these parallel pressure forces into a single resultant pressure force, and with some with the location and also with the direction. So if we can find that, so we can make our design of this this boat very simple, because that we can just make sure that okay, for the body, this boat body, we just make sure that they are just strong enough to hold this single force at some location. Okay, so this is our task. Okay, so let me repeat it. Our task is try to find a resultant. So this FR is called resultant. Okay, resultant force. So FR is the resultant force. And if I denote this point O, okay, so O is called the center of pressure. Okay, so our task now is that for these two cases, we want to reduce this multiple pressure force on different locations to a single resultant force, and the point of application of this single force, we also need to find it, and which is called the center of the pressure. So this is our task. And how we do that? Yes.
I just had a question about the distribution on the plate surface.
Yeah, this one.
Yeah, right. So before, when we were discussing pressure, and we derived the expression for pressure in terms of density, gravity, and the depth, it makes sense as you get deeper, the pressure would increase. But I don't understand why the pressure would increase horizontally.
You mean horizontally?
Right. So why would the pressure increase horizontally? Vertically makes sense.
No, I think you're misunderstanding this picture here. So this picture basically means that this right arrow is the force, pressure force. Okay. This red arrow just means the pressure force, and the longer this arrow means that the larger the force. The longer this line means the larger the force. Okay. So above this liquid surface, okay, above this water surface, we will have this universal pressure force, which is 1 atmosphere times this surface area. So that is this length, and after you go to the water, okay, so you have the additional this length here, additional this length here, additional this length here, additional this length due to this rho gh, and it's because it's going, this h is going deeper, so make this pressure force bigger. So that's why you see this like a triangle form to make it larger. It doesn't mean that this is longer is due to this force is longer on horizontal direction because your gravity is still on the g direction. Okay, this just means we just try to draw this force with a longer line to represent that the overall this pressure force is become larger.
Oh, okay, fine. So it's just to denote the pressure increasing in the vertical, not the horizontal. That's whatever. Okay.
Yeah.
All right. Thank you.
Yeah. So that's why is that it's starting from here, and also this line here is still the 1 atmosphere. So you can balance with 1 atmosphere on the other hand. So you can remove this one, and so the net force will be just equal to this triangle, profile. Okay. And how to do that? So we show you, right? So our two tasks, right? Task 1 is to find this resultant pressure force. Second one is that we want to find that where this center of the pressure will be, so that we can reduce all these different pressures to a single force on a point. So how to find that? So let's make the problem a little bit even generalized. Okay. So now let's assume that this plate is not vertical place. Let's assume that it's placed into this liquid, okay, with an angle. Okay, this angle is theta. Okay, theta angle, and so for these cases, okay, and when we can have similar thing, we can do drop this pressure force as we did before. Okay, so we have this pressure increasing on the surface. Okay, and remember this pressure force will need to be normal to the plate surface because that is the normal force direction. And so this is the pressure force view looks like. Okay, if the other side is also has 1 atmospheric pressure, so you can balance with this side to remove some length here. Okay, if there is not, okay, you can just using the full length. And so we found this what this FR, okay, resultant pressure will be. So how to find it? So let's first, okay, start it like determine the coordinate system. Okay, let's make this location as the origin point, or original point. Okay, and make this plate direction as the y-axis, and this is as the z-axis. So we also have x-axis from the vertical to this screen direction. Okay, so if you try to view this surface on the xy direction, okay, from the side view in this direction to this surface. Okay, if you're looking like this way, so this is the y direction, and you have another x direction in the vertical direction of the screen. Okay, and let's first, okay, let's do the similar things we did for this control volume system we did things before. Let's first try to study only a small element, this small element on this surface, and this small element has an area dA. Okay, and this element is defined by this length dx on the x direction and this length dy on the y direction. Okay, so we have dA has this dx dy as the length. So basically we know that dA equal to dx times dy. Okay. So what's the pressure force will be working on this surface? So the pressure force, okay, acting on this element will be just equal to, I'm working on this element just equal to dF equal to P times dA, right? P is the pressure at this location. Okay, and if we want to calculate the overall force, okay, all the force for the pressure force on the whole surface, we simply just need to integrate this equation, okay, on the whole area. Okay, so FR, so this will give us what the fully resultant force will be, okay? And you just integrate the pressure on the whole area. You know, this is very simple, right? Because pressure is stress, right? Stress integrated on area will give us force. So by this way, we can try to reduce all this pressure force to a single force point. Just integrate pressure on the whole area so we can know the magnitude, okay? This only give you the magnitude, okay? And also the direction is also known because the direction is always, because it's a flat plate, right? For flat plate, the direction, because the pressure force direction is always normal to the plate surface, okay? And also because it's a flat plate, so this normal direction won't change anywhere. So we can also know the direction. Because direction is always in this vertical direction to this plane. So by this way, you can quickly calculate this resultant force for both magnitude and direction. Okay, by using this integration on pressure on the whole surface area. Okay, and furthermore, okay, we can try to make this equation a little bit, you know, try to derive this equation a little bit more. We can write this pressure as a, you know, using this, you know, pressure depth correlation. Assume this pressure is equal to standard atmospheric pressure plus the rho gh. And also this h is this vertical distance on this to this surface area, right? So it will be equal to cosine theta times this y direction, right? So this is y level, y length, and this is theta. So this h will be cosine theta. Oh, sorry, so it's sin theta. So that means it's sin theta times this y. So h can be read as y times sin theta. So you bring these two into this resultant force. Okay, you can get this correlation here. Okay, just make it write it here, and also write this h as y sin theta. So you can further, because this y0 is constant, right? So you can make this term out. You can write this way, and also this rho g is constant. This sin theta is constant. You can take this rho g sin theta out. So your final result will be just equal to p0 times a plus rho g sin theta, do the integration of a times y dA. Okay, and what this it is, what this integration give you? Anyone get familiar with this one? From your statics class. You took those static class, right, before?
Moment of inertia.
Yeah, this is the moment of area, right? First moment of area, right? First moment of area. So this is basically give you YC, right? This is the Y coordinate, your centroid of this plate will be equal to A of this integration Y of dA, right? So in other way, you can write this term basically as this term can be written as this Y of C times A. And Y of C is the Y coordinate for the centroid for this plate. So you can further write this way. And your final result, maybe you can write in this form. Can write in this form. Rho g sin theta times VC times A, P3. And if you combine them together, and what this YC times sin theta will be? So assume that for this plate, this is their centroid. Okay, so this is their Y of C times sin theta basically is this value. So this will be H of C, which is the depth, which is the vertical depth of this centroid point, right? So you can further write this sin theta YC to HC. Okay, and what is P0 plus rho g times this HC? This is the absolute pressure of at the centroid, right? So this is P0, right? 1 atmosphere plus the depth. So this is basically, you can further write this part equal to PC. What does PC mean? This is PC is the absolute pressure in the liquid at the location of the centroid of the plate. So by this way, okay, you can quickly calculate the resultant pressure force simply will be equal to P of C. You know, first you find that where your centroid for that plate. Okay, then you find that what's the depth for that centroid, and you calculate using this equation to calculate what's the absolute pressure at that point and times the area. So you can get what the resultant force will be. Okay, so this is the result. So I will just stop here. So next class we will do more, try to finish this analysis. Okay, remember that right now we only finish try to find this resultant force, right? We still do not know that where that center point of this pressure force will be. Okay, I can tell you that for this pressure force, this center point of the pressure is not on this centroid location. Okay, it's not on this centroid point. It's on some other places. So next class we will try to find that. All right, so I will finish here. Do not forget your homework will be due tonight. So we will not have new homework right now, but I will assign new homework next Monday. Okay, and so if you have any question, you can ask me now. If you do not have any question, you know, we will finish here. Anyone? Any question?
Yeah, I have a question about something we did last class. It was the shear stress. I'm not 100% sure of the convention, the sign convention of.
Okay. So I didn't write it here, so let me quickly draw it. So you know, so the pressure force, right? So for the normal pressure, right? So it's like a normal pressure is dependent on, this is surface area N, right? And maybe you have a fault here. Okay, fault here. So for normal direction, this is the Y location and one delta YY, right? Because this is positive Y direction surface and also have Y direction fault. For this value, for these cases, it will be negative value. Why? Because this normal direction force and this fault direction, they are not on the same direction. Okay, if they are on the same direction, then it will be larger 0. So this is for normal force. For the shear force, okay, assume that this is normal direction Y, okay, N direction. And if I have a force on this direction, okay, so you mean we have a tau, this will be tau yx, right? Because this is the first is for the surface and the second for the direction. For the y, so this is a positive direction, right? Plus. And for the x is for the fault direction. And we see this force is going left, is the inverse, x is negative. So this plus and negative, they are not the same sign. So this will be smaller than 0. So it does only depend on these two, right? Yeah, so for this case, it's if it's going down, so this is positive sign because this surface is going to positive direction, and this is y is for the fault direction is go to negative direction. If you have this plus minus or minus plus, if their sign is not same, it will be smaller than 0. But if you have this tau yx delta xx something, if both these two signs either plus or minus, or if the plus or minus, if they are the same sign, then it is larger than 0. You understand what I'm talking?
Yeah, I understand what you're saying. Also, so like, for example, question 1 for the homework, the fluid was acting on obviously the bottom plate and the top plate. So in that case, if the fluid is flowing to the right and the normal of the upper plate is going down, we would have a negative y and a positive x. So the shear would be minus, right?
Yeah, sorry, I forgot this was problem. But,
okay, it's fine. So like, yeah, so you drew that. Now your coordinate system y would be pointing down, right? That would be a positive y.
Yeah.
Okay, and then your positive x is still going to the right.
Yeah. So I think it's more easily to another way to understand this is that if it's normal force, okay, if you try to compress the fluid, like the pressure is always negative value for normal force. If you try to going out, okay, to make this fluid going out to try to expand it, to try to expand its force is always larger than 0. Pressure tensor is always less smaller than 0, the negative one. So this is for normal force. And for the tensor force, okay, so if you try to your stress force is try to rotate. If you look at this stress force, right, you try to rotate this. Think about it, if you put this force, it's like you make this fluid has deformation, like some rotation, right? So if you like try to make it rotate in this clockwise, it will be positive value. If you try to in the other direction, you want to make the force on this way. You try to make it counterclockwise, it will be negative value. You understand what I'm talking?
Oh, so counterclockwise is negative?
Yeah, so this is another method to think about this, okay?
Okay, fine. So then the reason why I was confused is because there was a problem that our recitation TA gave us in which, like, if you go to the left, what you drew.
I see. So for that problem,
yeah.
I will let him to go through it again, okay, before the exam. So we will have a real section for that one. So I will try to make it clear, okay?
Right. No. So what I'm asking is the coordinate system on the bottom plate. If y is facing up and x is facing to the right, the coordinate system on the upper plate would be the reciprocal of that.
Yeah. Okay.
Okay. So I'm saying that's the notation we're taking.
So this will give a negative value tau.
If the fluid's flowing to the right.
Yeah, fluid going. I understand. So if you have fluid going to right, okay. So we want to see the force on the plate, right? So the plate will, for this one, will receive force on this direction, right? Sorry, I mean this. So receive force on this direction.
The other, right? Yeah.
You get this force. So this will be tau yx, and the y is going to negative direction, so it's minus. X is positive direction, positive. So this is smaller than 0. Because this is positive x direction, right? This is negative y direction. And on the top one, on the top one, I don't know. On the top one, if this plate, you try to drag this one. So on top one, maybe this way and this way. So on the top will be, it's also tau yx, and the y is negative, and on the plate, right? So sorry, on the plate it should be a positive. I make a mistake. So this is plate normal direction. So why are we using plate? This looks weird. Because plate normal direction, it should go in the up. This is should be normal direction on the plate. It should be going up with something like this. So this is the y is positive, x is normal, negative. So it will be also negative. Yeah, this way. Because you are looking at how the fluid working on the surface. All right, so I have to finish it here. Okay, so if you have more questions on this one, you can talk to me on next Wednesday, okay? On my office hour.
All right, thank you.
No problem. Okay, I'll see you guys.